Hello and welcome to today's webinar from Peak Scientific. My name is Ed Connor and I'm the product manager for Peak's precision products, which are gas solutions for gas chromatography. And today's webinar will look at helium method conversion for GC, and it follows on from our previous webinar where we looked at the main processes involved in converting methods from helium to hydrogen. Today I'll be giving you some application examples to show where we've worked with customers to go through the process of method conversion. So when we talk about converting to alternative carrier gases, we're really looking at nitrogen or hydrogen as alternatives to helium. Now, nitrogen can be used in a number of cases, but there are a couple of potential negatives when we look at nitrogen. So to start with, nitrogen has a low optimal velocity, which means that if you run at higher velocities, you can lose some peak resolution, so you can end up with poorer quality of chromatography. Now, it's not always the case, and there has been some very interesting work done by Restec where they've looked at equivalent analysis times by changing the column but using nitrogen instead of helium. On the plus side, nitrogen can be cheaply produced, so it can, for example, be generated, and it is inert, which again is an advantage and makes it quite similar to helium. When we look at hydrogen as an alternative to helium, hydrogen has a high optimal velocity, meaning that you can run the gas more quickly than helium without sacrificing separation of your sample. It can also be generated from deionized water using a generator, so it can be safely produced, but it can also be, or it's a reactive gas, so it can also react with your samples. Now, just to take a closer look at using hydrogen as an alternative to helium, if we look at the graph on the right, this is a Van Deemter plot which shows the efficiency of separation of hydrogen, helium and nitrogen across a range of flow rates through the column. And what you can see is that as we speed up the flow of gas through the column, the efficiency starts to drop off. Now, it's slightly counterintuitive, and so what we're aiming for is the bottom of the curve represents better separation of sample, and so as the curve steepens, this means that we're getting worse separation of sample. So with nitrogen, we can see that separation starts to become worse once we start to speed up to 20 or 30 centimeters per second. And with hydrogen, in comparison to helium, you can see that as we speed up the flow of gas through the column, the loss of sensitivity is not as great as we see for helium, and this is why hydrogen is referred to as a fast carrier gas, because it has a large range of flow rates across which it can separate samples very well. So if we look at the typical linear velocity range of helium, which tends to be 30 to 40 centimeters per second, if we run samples using hydrogen carrier gas across this kind of linear velocity, we tend to see slightly better efficiency, so we see slightly better chromatography results. So we get improved resolution, improved peak shape, and so the characteristics of hydrogen do actually mean that revalidating methods to use hydrogen can provide some very good results. So there's also the opportunity to run samples at lower temperatures whilst achieving similar results, and this can have knock-on effects such as prolonging column lifetime, because the column will not need to be heated up to as high a temperature. And for any labs who are looking to decrease the overall analysis time, by heating up to a lower temperature, the cooling down period is reduced, so the time between sample injections can be reduced. So not only can you reduce your analysis time, but you can also reduce the time between sample analyses. Okay, so in the last webinar, we went into some detail to look at method translation and the key considerations. This slide really just gives you a very brief overview of the key considerations when looking to change carrier gas. So first of all, checking that the methods you are running can be changed, because there are certain methods that are not compliant if run with a different carrier gas. Things like checking your vacuum pump if you're using GCMS, to make sure that it is efficient enough to be able to vent away the hydrogen carrier gas entering the mass spectrometer. Also researching your methods and looking at examples, so application notes or papers or any other materials where there are examples of the analysis that you're looking to carry out to be having been done. Then looking at your gas supply. Now at Peak we make gas generators for GC, and generators are a very good and safe and reliable source of gas that you can use to take away a number of the issues associated with gas supply. Then on to method translation, and using method translation software to check your new method settings. Again, when looking at the key considerations, there are likely to be some challenges, and we'll cover some of the potential challenges that you may face in the application examples that I'm going to present afterwards. And of course, if you are changing your methods, then you will need to update SOPs and any associated paperwork. So again, it's just something to keep in mind, that it's not as simple always as just changing the gas and carrying on with your analysis. So we will now look at our first application example. So this is on FAMES analysis, fatty acid methyl eth. So FAMES analysis is commonly used in food and beverage analysis, although it is used in other types of analysis as well, such as oil and gas. But this particular example was from a food and beverage lab, and the study focused on a 39 component standard mixture of FAMES, and the customer was changing from helium to hydrogen for this GCFID analysis because of supply issues and price increases that they had been seeing. So I have the conditions used in the analysis in the table on the right hand side. So the original method used helium, so you can see the conditions there, and you'll see on the right two columns we have hydrogen carrier gas, and we have different linear velocities shown, and one of them you will see is very close to the linear velocity used in helium, and this will all become apparent in a minute as to why we have these two different speeds of analysis in this method. So looking at the helium method results, we have all 39 peaks resolved on the chromatogram. There is one region that is slightly less well resolved, and so this was a potential point of concern when we were looking at cutting the method. And you can see the peaks here labelled numbers 29 through to 33 are not very well resolved at all. And so what the customer basically looked at converting the method, but obviously with a keen eye on this area of the chromatogram. So carrier gas was switched. All the hardware on the GC remained the same, so the same column was used. They did change the septum and liner, but the system was more or less unchanged, and the carrier gas was just changed in the software. And so the corresponding method was slightly shorter, 5 minutes shorter than the helium analysis time, but that region of poorly resolved peaks did in fact show us coelution of the peaks. So these peaks 29 through to 33 ended up coeluting into 2 peaks instead of the 5 that we had with the helium method. So to make the method development simpler, the customer decided to match the linear velocity of the method using hydrogen to that was used when helium was the carrier gas. And so this was achieved by lowering the inlet pressure. So because hydrogen is more viscous, to achieve the same linear velocity of gas through the column, you require less pressure to get the same velocity through the same column. And this lower inlet pressure actually reduced the analyte transfer onto the column. So because the customer was using split injection, they were able to reduce the split flow to increase the concentration of sample being injected. Another or an alternative to this would be to use pulsed pressure injection, and this can be a way of improving the transfer of the sample onto the column when using hydrogen, and preventing reaction between hydrogen carrier gas and your analytes. But in this case, because there was a high enough split ratio, then this was reduced and the split flow was reduced. So if we look at the results of the revalidated method, where the linear velocity of hydrogen was matched to that of the original helium method, what we can see is that the peak shape has improved, and so the peak height is higher in this sample, and all 39 peaks resolved, as you can see here. So we've basically got like for like analysis, but we're using hydrogen instead of helium. And just to show you that relative increase in peak height, you can see the 2 chromatograms side by side on the same scale. So we have a clear improvement in the chromatography using hydrogen carrier gas, and really this is because hydrogen is giving us better performance when it comes to the separation of the sample. So we're getting sharper peaks and better peak shape overall. Now the analysis time is identical, so even though, as I said earlier in the presentation, hydrogen is considered as a fast carrier gas, and often one of the main attractions may be to try and increase your analysis or decrease your analysis time. A good place to start when revalidating a method is in fact to follow what was done here and match the linear velocity of your hydrogen method to that of your helium method. And one of the key reasons for doing this is that, especially with detectors such as FID, it means that all of your peaks will elute at the same retention time. so you are able to make sure that you've recovered all of the sample at the same time, and you can do a direct comparison between the analysis you were doing with helium compared to hydrogen. It's then, of course, possible to look at improving the method and maybe playing around with the settings to try and speed up analysis. And just to show you in a bit more detail the results of the poorly resolved peaks, you can just see there that the separation is almost identical for the two carrier gases. Okay, so now we will look at our second application note. So this one is on detailed hydrocarbon analysis, or DHA, and this time we're looking at an ASTM method. So it's method D6729, and so at the beginning when I said about the key considerations, methods such as ASTM methods are only compliant if they have been validated for use with an alternative carrier gas. And so ASTM D6729 does have an appendix allowing use of hydrogen as a carrier gas as an alternative to helium. So DHA analysis looks at PONA constituents in gasoline. So these are paraffins, olefins, naphthalenes and aromatics. And run times can be quite long, so they can easily exceed 2 hours. And so one of the attractions of using hydrogen for this method is the potential to reduce the analysis time. So the table on the right hand side shows the method conditions. So you can see we have hydrogen supplied by a peak hydrogen generator, and the original method used helium from a cylinder. The split ratio is quite high, so it's a 250:1 split, so the consumption of gas is very high. So again, when it comes to trying to conserve helium, methods like this are of course a good way to save lots of gas for any analyses where you don't have alternatives. You can see the column flow on the hydrogen method is higher than on the helium, so we have 2.5 milliliters per minute versus 1.8, and the corresponding oven ramps are have much shorter hold times and a higher ramp rate, which ultimately means that the analysis is much faster. So if we have a look at chromatograms, you see the helium on the top and hydrogen on the bottom, and there's a considerable time saving when using hydrogen. So getting a 40% time saving, 32 minutes shorter using hydrogen than helium. Now, of course, as we saw in the last example, it's all very well being able to run samples faster, but you need to make sure that all of the peaks of interest are separated. Now, there's one critical separation in this method, which is the separation of 1-methyl cyclopentane and benzene. And if we look at, if we zoom in on the chromatogram, you can see the two peaks there, and actually on the top trace, which is helium, the separation of these two products is actually not as good as we get with hydrogen carrier gas, despite the fact that the hydrogen carrier gas is flowing through the column at a much faster rate. So we're getting improved chromatography and saving time, which is exactly what we would want. So the table on the right hand side shows a comparison of the different groups analysed within the analysis, and just to look at the hydrogen and helium recovery rates, and there was no significant difference between any of the products that are being analysed in this analysis. So we're getting like-for-like analysis, but we're seeing a 40% time saving. So for any labs who are carrying out DHA analysis, this is a very good opportunity to save a lot of time, and for any contract labs doing this analysis, of course, then this can be converted to increased revenue. So if you need more details, then this application note and all of the others that I'm discussing in the webinar today are available on the Peak website. So our third and final application note example today is on essential oils analysis. So this relates more to flavours and fragrances. And this method is a GCMS method. And just to remind you, or to highlight a couple of points regarding GCMS method translation. So GCMS method conversion is known to present more challenges than GCFID. So there are things to consider, such as hydrogen potentially reacting with analytes, which I mentioned before, can be overcome by using pulsed pressure injection. There are also some instances where library search functions can be affected because of reaction between hydrogen and sample, causing changes to fragmentation patterns. And also sensitivity can be reduced when we look at hydrogen in comparison to helium. Now, there are some method tweaks that can overcome some of these challenges. So when we look at sensitivity, for example, using SIM, so selected ion monitoring detection, or a combination of SIM and scan, can allow improved sensitivity on GCMS systems when using hydrogen. Also, reducing the diameter of the column that you're using for analysis will reduce the amount of hydrogen entering the ion source, which again can improve results in the source. Also, preparing your mass spectrometer to reduce the potential effects of hydrogen by looking at alternative lenses, and this application note actually concerns this point specifically. And I mentioned using pulsed pressure injection. So another thing just to consider, and this actually also is a point that needs to be considered when changing carrier gas from helium to hydrogen on any GC system, regardless of the detector. Changing the tubing of from the original gas supply over to your hydrogen generator can result in significant background showing on the GC. So it's really advised to change the tubing, so to use brand new tubing, stainless steel if possible, from your hydrogen generator to the GC. Of course, replacing the septum and liner would be good practice. Normally changing the gold seal is not necessary, but it can be in some cases required, but not normally. And when changing to hydrogen, this has been highlighted by Agilent in particular, baking out the ion source can be important. So Agilent recommend to bake out the ion source at high temperature with the filament on overnight, and this has a good effect of reducing background. And the chromatograms that you can see on the right hand side here, this is an overlay of the same essential oils mixture being injected on day after day. What we can see is that from the third day onwards, after changing from helium to hydrogen, we see the baseline has settled to a constant background level. But there can be higher background initially after changing carrier gas. So this is just something else you need to consider if you are looking at changing from helium to hydrogen, just to be aware that there may be some time required to reduce the background on the system. And there is additional information available from Agilent, specifically looking at the steps you can take to improve your experience when changing from helium to hydrogen. And again, on the Peak website we have lots of information as well. So on to the actual analysis and the aims of this study. So we did this in collaboration with a university in Sao Paulo in Brazil, and we were interested in looking at the effect of combining a larger draw-out lens, which is the component in the ion source of Agilent GCMS single quads, and looking at SIM detection, so selected ion monitoring detection. And we wanted really to see the effect of the larger draw-out lens and SIM detection, and looking at whether we could get comparable results to helium analysis. So we compared the results from helium and hydrogen carrier gas across a range of flow rates, and then we just assessed the results by looking at peak resolution and signal to noise ratio of essential oils. So the image here shows the draw out lens. So the instrument used here was a 5975 GCMS. On the newer Agilent GCMS, the 5977, there is an extractor lens, but it uses a similar principle, and again different sized orifices are available. So the standard size is the 3mm orifice, but there is a 6 and a 9mm orifice available. And for the purposes of this study, we used the 6mm orifice for hydrogen analysis and the 3mm for helium. So we ran samples across 3 flow rates, which I've labelled as optimal, less optimal and suboptimal. And we had helium with the 3mm lens and hydrogen with a 6mm lens. And we looked at results using full scan acquisition and selected ion monitoring, so SIM. And what we can see if we look at resolution, when helium is run at optimal velocity, we see resolution of 4.94 compared to hydrogen at 2.6, so it's certainly better when using helium in full scan mode at optimal linear velocity. But when we look at SIM detection, we actually see better results when using hydrogen across the full range of flow rates than we do for helium. So I think this is quite interesting, and so it really means that if you are able to set up your method to target analytes of interest using a SIM method, then you can actually get very good resolution compared to helium when using hydrogen in SIM mode. Now if we look at the bottom of the table and look at the signal to noise, when we look at full scan detection, we actually see a huge drop off when we're looking at hydrogen in full scan mode. So typically Agilent say that we can expect to see a 2 to 5 times loss of sensitivity. When we look at the signal to noise here, we're actually down to a tenth in full scan mode. But interestingly, in sim mode, then we're actually getting very comparable results when we are running both either helium or hydrogen at optimal carrier velocity. So really this all points to using sim detection where possible for hydrogen. And just to summarize the results that we saw, so at optimal flow rates, hydrogen carrier gas in full scan mode can give poorer resolution, and a reduction in signal to noise was clearly seen in this case. But although the signal to noise was reduced when we looked at in full scan mode, when we were looking at sim detection, then we saw better resolution using hydrogen than helium. And another point is, of course, this will all depend on the concentration of the analytes that you're looking at. So if you can afford to sacrifice some signal to noise, then hydrogen, of course, will be perfectly applicable. If you're looking at ultra trace levels of analytes, then it may be that hydrogen is not possible to be used for your method. Again, just one other point to add is that different compounds behave differently when using hydrogen carrier gas. So again, it's important to look at performance of the analytes that you're specifically looking at, and again, back to the point about researching, it's important to look for any examples of the analysis that you're doing and seeing whether anybody else has used hydrogen for that. And just to reiterate that point on sim detection, hydrogen carrier gas can give very similar signal to noise results to helium carrier gas in sim mode. And so for targeted analysis, I would say that hydrogen is definitely a good alternative to helium for GCMS analysis. Okay, so those were the 3 application examples. They are all on the Peak website, so please, if you want more detail, please go and have a look at those and download them. To summarise what we've covered today, looking at converting hydrogen carrier gas should certainly not be done without expecting some challenges. Generally speaking, GCFID method conversion is simpler. Of course, there could be some difficulties involved, but generally speaking, it's easier to achieve without having to make big changes to your setup or to the method. When we look at GCMS, it does tend to present more technical challenges, but it can offer significant reduction in analysis time. It will help you to reduce helium consumption, and as we just showed in the last application example, by making adjustments to hardware and your acquisition settings, you can actually get very good comparable results using hydrogen in comparison to helium. Right, so that brings us to the end of the presentation. We do have a live Q&A which will be open in a second, so if you do have any questions, there's a question mark at the top right hand side of your screen, so please do feel free to click on there and type any questions into the chat box. Otherwise, if we don't have time to cover everything today, if you do have any questions that we don't manage to get to, then please email discover@peakscientific.com and we will get back to you. But now we'll start to look at the questions that have already been put into the chat.